Yes, Assalamualaikum warahmatullahi wabarakatuh, and a very good evening to everybody. Okay, now we are in the last topic, yeah, moment area method for deflection. This is actually part of the topics in deflection of beam, yeah, but this method is not so popular, and normally it's not used, and also it's not asked in a test or exam. So yeah, I put it in the last part of the lecture. Okay, moment area method is one of the four methods that we use in the analysis of deflection of beam. The first one is the integration method or double integration method, yeah, which we have done in lecture and the topic of deflection of beam, and then followed by the Macaulay method, which is the modification of double integration method. And we also have done the unit load method or virtual work method. The same method that we use for thrust analysis, for the analysis of thrust member forces and also deflection. And this is the fourth method for deflection of beam, moment area method. So what is moment area method? Okay. So moment area method is based on the properties of elastic curve and bending moment diagram. So what is bending moment? What is elastic curve and bending moment diagram? We have done it in deflection of beam using double integration and also unit load method. So this is not something new, yeah, but we use in different approach, yeah, by using moment area method. And the advantage of this moment area method, yeah, it is suitable for use for determining the deflection and slope at particular point. And also, it is suitable for beam with different cross-section. If we remember, yeah, for double integration, a Macaulay method, it is not suitable for different cross-section. But for unit load method, it is yes, yeah, it is suitable for different cross-section, and it is a moment area method now, which is also suitable for different cross-section. So in this method, yeah, it is based on two important theorems. Yeah, important theorem, which is the first theorem. It is stated that the angle between the tangent at any 2 points on the elastic curve, this is elastic curve. Yeah, this is the elastic curve. Why it is called elastic? Because yeah, our analysis is based on elastic zone, yeah, not plastic zone. So we are working between the small deflection. Elastic zone is for small deflection. The tangents at any 2 points, point A and B, yeah, in this figure, on the elastic curve equals the area under the M over EI diagram between these 2 points. This is MEI diagram. This is x-axis or distance, and this is the moment, bending moment diagram. Okay? Actually, this is what bending moment diagram. So EI d squared y dx squared is moment. The same thing that we have done in the last lecture on deflection of beam, and also on stress distribution, bending stress. Okay, this is the same theorem, the same formula. Okay, moment equal to EI d squared y over dx squared. Okay, but what is the d squared y and dx squared? This is d over dx dy dx. Yeah, you see here, this one, this d squared and dx squared. And now what is dy dx? Yeah, what is dy dx? dy dx is the slope. Here. So this is the slope. This is dy dx. Therefore, d theta, the slope, is equal to m over ei dx. You bring ei here, and then we have d theta equal to m over ei dx. Okay. This is because why? Because theta equal to dy dx. So d theta equal to m over ei dx. It is mentioned already here. So therefore, theta ab, theta ab, if we here, if we write the tangent between a and b, here, this is equal to m over ei dx, and over the ei dx integration between b and a. So this is mathematical expression. M over ei dx is area here. This one. M over ei dx, the width of this segment multiplied by the height of this segment. The height is equal to m over ei. So m over ei times dx is area. And the theorem said the area is equal to the tangent d theta. So what is the expression of this mathematical expression of this area is integration. How to find or how to calculate this value? If you split into small segment, 1, 2, 3, 4, up to 1,000, yes, you can calculate the area. But now, since we know the equation or the formula of m, therefore we use mathematical integration. If we do not know the mathematical integration of m, then we use numerical integration. So what is the integration here? Is the area between A to B. Area between A to B. Okay. Now, why it is not appeared here? As I mentioned just now, if we know the relationship between x and m over ei, then we can just use numerical integration. Okay. So this is now d theta. D theta. Or in between dx. Okay. So this equation forms the basis for the first moment area theorem. This is the first moment area theorem. Where theta AB, theta AB here equal to integration m over ei dx here. Integration m over ei dx between xb and xa. And it is equal to area of this segment between A and B. Area of between A and B. What is the area under the bending moment curve? This is the tangent or the slope between A and B. Now this is important theorem that we will going to use in deflection of beam. It is now not deflection. This is the tangent. We use this tangent between A and B to calculate deflection later on. And it is done through theorem 2. Theorem number 2. This is now deflection. the vertical deviation of the tangent at point A on elastic curve with respect to the tangent extended from another point B equals, what is elastic curve? Again is this one. The deflection is the elastic curve. Equal the moment of the area under the M over EI diagram between these 2 points A and B. This moment is computed about point A, where the vertical deviation TAB is to be determined. Okay, so we have two theorem now, yeah, which we will use because we integrate the two theorem, yeah, into the calculation of deflection at any point, yeah, along the beam. Okay. So from the theorem 2, the vertical deviation of the tangent at A here, this vertical deviation, TAB is the vertical deviation with respect to the tangent at B here is given as TAB, that means TA in respect or in relation or in comparison with B is equal to integration of M over EI dx times X. What is M over EI dx? This is the moment area. And what is X multiplied by this one? This is the first moment area. Yeah, first moment area. Okay. So that then TAB equal to, yeah, XM over EI. Yeah, since X is constant, yeah, so we take out X here. Yeah, just integrate M over EI dx. Yeah, integrate M over EI dx. EI is actually constant, so EI can be taken out here. Then we just integrate M dx. M is not constant because M varies with dx. Yeah, what constant here is X and EI. Why it is constant? Because X is the centroid of moment area between A and B. So it is constant. Okay. Yeah, where X is the location of the centroid of the shaded area. Yeah, or we call it area under the MEI curve between A and B. Okay. So again here, when we use integration here, yeah, if we use the mathematical formula of M and dx, we use integration formula. Okay. But if we do not use, we do not know the integration, the mathematical relationship M dx, yeah, maybe it is triangular or rectangular, yeah, then we use numerical integration. When we use numerical integration, we don't use this mathematical integration anymore. Yeah. So what we are going to use in this moment area method is just numerical integration. Yeah. Okay. So this is what I mean by yeah, numerical integration here. Where yeah, it is known already the shape of the moment. Yeah, it is known already. So we just calculate the area without using mathematical integration. We can just calculate what is the area. The area is equal to BH over 2. This is the area of triangular. And what is the centroid? The centroid is equal to, yeah, 1/3 of the height of this triangular. And what's about this one? This is the moment diagram for point load. for moment diagram for uniformly distributed load, this is in the form of parabolic. Parabolic. So for this one, A equal to BH over 3 and X equal to B over 4. And this is the formula given here. A equal to BH over N plus 1 for triangular N equal to 1, and for curve, for curve N equal to 1, N equal to 2. So area equal to BH over 3 here. And the centroid is B over 4 when N equal to 2. So what is N? Why it is equal to 1? Why it is equal to 2? Here N equal to 1, here N equal to 2. You can refer to the textbook. It is based on mathematical curve, right? Mathematical curve relationship between M over EI and X. Okay. Now, equal state to example 1. The beam shown in the figure is pin supported at A and roller at B. A point load of 60 kilonewton is applied at 6 meters in the middle of the beam from A. Determine the deflection at B, or maximum deflection in this case because it is symmetry. So for this symmetrical type, we can just calculate the reaction. Just dividing 60 over to 30 equal. Okay, what next? Of course, next stage is to draw bending moment diagram. Because it is moment area method. Do bending moment diagram here. Okay, but before that, the deflection and slope diagram of the beam. Reference point is taken from A. Okay, so now what in the question is to find the deflection at B. Deflection at B. Now, we use A as a reference point. In this case, A is at the support. But don't use reference point here because we do not know the position of this point. The condition of this point. But A, we know the condition of this point, the properties of this point is it is zero deflection. And moment equal to 0 here. Okay. Okay. This is the elastic curve of deflection, where at this point B, the slope is equal to 0 and the deflection is maximum, YB. If you draw your extrapolation of this slope at A, the slope at A, you draw here. Okay. So here is TCA. Here is TCA. What is TCA? TCA is the tangent in relation to tangent at A, to the slope at A. Okay, TCA. And here is TBA. What is the relationship between YB, TBA, and TCA? Okay, from the figure, YB plus TBA equal to BB dash. Therefore, YB equal to BB dash minus TBA. And from this figure also, we know that here, BB dash divided by 3, because this is the same identical triangular, BB dash divided by 3 equal to TCA divided by 6. This is trigonometry. BB dash divided by 3 equal to TCA divided by 6. And therefore, BB dash equal to TCA over 2. Or in other words, BB dash is equal to half of TCA. It is clear here. Yeah, it is half of this TCA. But remember, the BB dash is not the deflection. The deflection is YB. Yeah, is YB. Okay. This is the moment diagram. Yeah, the moment diagram. 60. Yeah, sorry, 90. 90 is what is 90? 90 is 60 times 3. Oh, sorry, times 6 divided by 4. WL over 4 equal to 90. 60 times 6, 36, 36, 360, 360 divided by 4, 90. And this is the maximum moment at mid distance. Yeah. Okay. Now this is the formula, yeah, that we have to understand in this method of moment area. Yeah? This is the formula. So now how to understand this formula? Yeah, it is based on theorem 1 and theorem 2. Yeah. TBA. What is TBA here? What is TBA? What is TCA? TBA is equal to first moment area. First moment area, or moment area multiplied by centroid distance. What is mean here? This is the area. Yeah. Half times 2, times 3, times 90, times distance. Centroid. What is TBA? TBA, B in relation to A. What is TCA? TCA is C, yeah, in relation to A. So if we say TBA, that means, yeah, the area is between B to A. And, yeah, and the centroid distance is from B, not from A. This is what we, that's why, yeah, I said just now, this is the most important formula here. What is TBA and what is TCA? Not TAB, but TB in relation to A. When we say TBA, that means, yeah, the area between A and B, but the most important is that the centroid of this triangle from B, not from A. Yeah. So 3 divided by 3, what is that? Here. Equal to 135 over EI. And this one is TCA. TCA is, yeah, C in relation to A. Therefore, calculate the area under the bending moment between A and C, and then the first moment area between C in relation to A. So, yeah, in this case, we divide this triangular into two, 1 and 2 here. Okay, yeah. So here between B and A, half times 3 times 90 times 3 divided by 3 plus 3. Why plus 3 here? 3 plus 3 divided by 3 for this area, and for this area, yeah, it is half times 3 times 90, but this is the centroid, 2/3 of 3 here, equal to 810 divided by EI. Okay, and then we apply this, yeah, illustration, the relationship between TBA and TCA. Then we got BB dash equal to TCA over 2. It is, yeah, we have it now here. BB dash equal to TCA over 2 equal to half times TCA. TCA is equal to 810 divided by EI equal to 405 over EI. And from this equation also, we have PB dash equal to TCA over 2. Here, sorry, here. Where is it? Oh, it's not here. Sorry, yeah. Here. YB equal to BB dash minus TBA. YB equal to BB dash minus TBA. Okay. But BB dash equal to 405 over EI. Therefore, YB equal to BB dash minus TBA here. And what is TBA? 135 over EI. Therefore, YB equal to 270 divided by EI. And if EI is given as 30,000 here, or not given here, if EI is given as 30,000, therefore YB equal to 9 millimeter downward. Yeah, because positive. We assume YB as positive here. We assume here YB. Therefore, it is positive. But therefore, it is downward because it is positive. If it is negative, that means, yeah, it is opposite to what we assume. Okay, now, if you remember, yeah, the formula for deflection of mid-span loading using double integration, using Macaulay method, using unit load method, yeah, we have proven that all the three methods got the same answer, same formula, WL over 48 EI. And now, what's about this method number 4, moment area method? You can prove here. Yeah? Compare with double integration method, Macaulay method, and unit method, you got WL to the power of 3, 48 over EI. If you use this formula, you get the same answer. So that means this moment area method is another method which we can compare and which can be used as verification to the other methods. And also, yeah, we have found here that all the 4 methods are exactly the same answer. Okay, if you want to prove this formula using moment array method, you put 60 as W, here is L, and yeah, and you derive the formula, you will get the same answer, WL to the power 3 divided by 48 EI. Okay, let example 1. Okay. Example 2. Yeah, we have only 2 examples for this last topic. The beam shown in the figure is being supported at A and rolled at B. A point load of 60 kN is applied at 6 meters from A. Determine deflection at B, slope at B, and maximum deflection. We do not know, yeah, we don't know actually where, which point, yeah, that have maximum deflection. Okay, what should we start now? Start with the moment diagram. Yeah, moment diagram here. But before that moment diagram, we have to start with the elastic curve. Yeah, elastic curve. You remember in if we use double integration, unit load method, Macaulay method, yeah, we don't have to sketch this slope or elastic curve. But for this moment array method, we have to sketch first, because from this sketch we can develop the mathematical relationship between, yeah, YB and TBA. Okay, yeah. So now, what is the mathematical relationship? YB equal to TB dash minus TBA, the same question, the same equation. But in this case, BB dash is equal to 1/3 of TCA, or BB dash equal to TCA over 3. In example number 1, in example 1, BB dash equal to TCA over 2. But in here, BB dash equal to TCA over 3. That's the difference between example 2 and example 1. Okay, next. So this is the moment diagram. But we can also, yeah, divide this moment diagram into 2 and then overlapping each other. Yeah, or this this is due to the loading, this one 60 kilonewton, or this is due to VA equal to 20 kilonewton here, and this one is due to P 60 kilonewton. Okay, if you are here, yeah, if you are here, moment area is due to reaction and 60 kilonewton here. If you are here at C, why at C? Because, yeah, we want to find TCA. If you are at C, moment area is due to 20 kilonewton and 60 kilonewton. Therefore, that's why we use 2 area. But you can also, if you don't like this method, use this method. This is the actual bending moment. This one is the bending moment, yeah, but we split into 2. But actually, the resultant of this, yeah, area is actually equal to this one. Yeah, so yeah, it is up to you. You want to use here or you want to use here. If you use this one, yeah, TBE, TBE equal to what? You are at B. When you are at B, what is the area? The area is equal to 3 multiplied by 60 divided by 2. This is the area of moment multiplied by the centroid. Yeah? Area times centroid equal to first moment area. The centroid of this triangular is 1/3 of distance, therefore equal to 1, 1/3 of 3. This is BA. Yeah, this is BA. Why BA? Because what we want to know is deflection at B. Yeah, deflection at B. Okay? Why B? TBA. That's why we calculate TB in relation to A. And what is TCA? Yeah, TCA is the first moment area at C, yeah, in relation to A. Yeah, TBA, B in relation to A. Why we want to know TCA? Because here, yeah, BB dash equal to TCA over 3. So we want to know TCA. So TCA, okay? TCA, there are two moment area. 1, 2. This one, the area is equal to 9 times 180 divided by 2 times centroid. Centroid of this triangle is here. And this one is negative. And the area is 380 divided by 2 times the centroid. And centroid is equal to 1/3 of this height, equal to 1. So use negative here. Equal to 2160 over EI. Okay, the question, can you can you get this answer and this answer using this method? So this is your homework. You can try. Yeah? You can try, and I have tried this option. Yes. Yeah, you will get the same answer. You use this one. Similarly here, this one. In this case, you use the actual bending moment diagram. Can you use the superimpose method in this case? In this method, yes, and you got the same answer. So for this example 1 and 2, I show two methods. In example 1, I use the bending moment diagram, the resultant bending moment diagram. In example 2, we use superimpose bending moment diagram. But of course, when you compare this method, this alternative method, you'll get the same answer here. Now, next, what next? We know that BB dash equal to, here, we know that BB dash equal to TCA over 3. And what is TCA? TCA is 2160 here, equal to 270. And we also know that YB equal to here, YB equal to BB dash minus TBA, therefore equal to 630 over EI, and if EI 30,000, YB equal to 21 millimeter. Answer. Okay, And what next? Slope at B. Yeah, slope at B. Okay. So for the slope at B, yeah, we know that theta A here, where is it? Sorry. Yeah. Yeah, okay. We know that theta A equal to theta AB, theta AB plus theta B. This is again trigonometrical relationship. Tau AB is the angle made by this extrapolation to the horizontal, tau AB, or the slope at A. Tau B is the slope at B, and tau AB is the difference between slope at A and slope at B. Or in other words, theta AB equal to theta A minus theta B. Theta AB equal to theta A minus theta B. Okay. Again, trigonometry. Theta A is equal to tangent theta A. What is tangent theta A? Tangent theta A equal to TCA here divided by distance. But TCA equal to 2160 over 3. Therefore, tangent theta equal to 2160 over 9. Sorry, TCA is equal to 2160 here. 2160. Therefore, equal to 2160 divided by 9e. Okay. And what is theta AB? Here, theta AB. Theta AB is equal to half 3 times 60. Moment area. Moment area. It's written here. Theorem number 1. What is theorem number 1? This one. Here. D theta equal to moment area. D theta equal to moment area. Theorem number 2 is about the diffraction. Theorem number 1 is about the slope here. So now we use this equation here. Okay, the slope equal to moment. Sorry, the area under moment diagram here. Equal to half 3 by 60. Okay, what is 3 by 60 here? 3 by 60. The moment. Equal to 90 over EI. Therefore, theta B equal to 2160 minus 90 over EI. What is this? This one. Theta B equal to theta A minus theta AB. Then equal to 150. So if EI equal to 30,000, theta B equal to 0.005 radian. Now, again, you can prove this answer using Macaulay method, using unit loop method, using double integration method. And what next? Maximum deflection. Okay. Now, in first example, maximum deflection is at mid distance. But for this example, example number 2, we do not know where is the maximum deflection. Maybe here, maybe here, maybe here. Between B and C, we do not know. But for sure, what we know is that at the point of maximum deflection, the slope is equal to 0. So where is that point? Similar to double integration method and Macquarie method or unit loop method, yeah, you use try and error. Yeah, if you remember, we use try and error, and then we do interpolation. Yeah, try and error. Now in this case, maybe the maximum deflection is somewhere here, where the slope is 0. Yeah, let's say between x between 0 and 6. Yeah, x between 0 and 6. Okay, in this case, y max, yeah, again, this is trigonometrical relationship. Y max equal to mm dash minus tme here. And if it is x, therefore mm dash divided by x equal to divided by 9. This is identical triangular. So mm dash equal to x over 3 tce. Okay. And what is TMA? Yeah, TMA is the moment area, the first moment area. Yeah, equal to there's no bending moment diagram. Yeah, sorry. Yeah. So this is the bending moment diagram. X times 20, yeah, times x divided by 2. Oh, sorry, x times 20 divided by 2. It is moment area times centroid, yeah, and this is the first moment area equal to 10x to the power of 3 divided by 3 ei. Therefore, using again this relationship, yeah, mm dash here, yeah, x over 9, yeah, mm dash minus 10x to the power 3 divided by ei equal to y max. Okay, but it is not finalized yet because we do not know x. What is x? Okay, now we go to deflection. We know that, yeah, at maximum deflection here, slope equal to 0. Yeah, slope equal to 0. Then from equation 3, what is equation 3 here? Here, okay, dy dx. Dy max dx equal to 1 ei 240 here. 240 minus 10x divided by 3 equal to 0. Yeah? Which, if we solve this equation, x equal to 4.9. Yeah, this is your homework. X equal to 4.9. And if x equal to 4.9, then substitute into this equation of y max, you got 378 and 785 divided by ei equal to 26 millimeter. This is the y maximum. So, okay, so this is the second example. Actually, there are more example. Yeah, example 3. Yeah, we also have example. Oh yeah, we can also compare. Yeah, this method. Yeah, for uniformly distributed loading here. what is the maximum diffraction? This should be the answer. Based on double integration, based on microLab method, and based on unit load method, you got this answer. Now, yeah, it is your homework. Try to use moment array method to get this answer. Yeah, it is not given here. Yeah, it is your job if you are interested to know more about moment area method. Okay, so for that, this is the tutorial that I have given to you, yeah, last time. Yeah, I hope you can do this tutorial and submit to me. Yeah, and also about the lecture, this is the last topic. Yeah, but as I mentioned in last time, yeah, since the performance in the test 2 is not so encouraging, yeah, not so good, then we need another question or another test, not test, but another short quiz, yeah, that you have to submit, yeah, maybe next week, yeah, to improve your career marks. Yeah, it is up to you. If you don't like that quiz, yeah, so you just depend on your test 2. Yeah, but I advise you, yeah, I strongly advise you, yeah, to do that quiz, to attend that quiz so that you can get higher marks, yeah, as a preparation for the final exam. Okay, yeah, so for that, thanks, yeah, thank you for your attention, yeah, and Assalamualaikum warahmatullahi taala wabarakatuh.